Hello everyone, it's September the 14th. Alright, first things first, before I started this, I just spent some time working on this. And you can see I worked from maybe a few, 20 minutes ago, 20, 30 minutes ago. And after two failed attempts, I got it. Okay, I got it. So I'll actually talk more about this later on. And I think this method probably is right, but we're gonna take a look at it, discuss anyway. But let's first deal with today's challenge. All right, so an integer array is transformed into a doubled array, changed by appending twice the value of every element in the original and then randomly shuffling the results array. Given an array changed, return original if changed is a doubled array. If change is not a double array, return an empty array. The elements in the original may be returning in order. So, yeah, times 2 times 2 times 2. Okay? I mean, for one thing, it has to be even number. And it has to at least have half to be all even values. So we can get all the even values out. Like the odd value must be, and we can give all even values. And then what do you do? Well, we can, we'll just multiply this by 2, right? We get this, and we multiply it by 2, and then see if there are half of it in this, right? Because they already multiplied. When you multiply it again, it definitely will not exist in this. So you just need to see if there exists half of it that's in the multiplied version that's going to be inside the original version. But I just have a question, such as you're saying we're going to multiply, all right? So let's say the original array is 2, 4, 8. All right, and the double 8 will be 4, 8, 16. All right, so this is the changed array. Okay, then you say we double it. Okay, we double it, what we get is 4, 8, 16, 8, 16, 32. This is what we get when we double the change. And then we go say 4 is in it, 8 is in it, 16 is in it, right? So we got 3. It should be only 3. Now we have repeats, but repeats, maybe it's fine. Yeah, so if we get more, what does that mean? Original, then we multiply, then we got more. Maybe divide is a smarter idea. Like seriously, divide is a smarter idea. Maybe we should divide by 2. If I divide by 2, then let's say all non-integer will become negative. So be -1, -1, 2, 1, 3, and 4. Right, so this is divided by 2. And then we kind of take a look. After divide by 2, we see how many we have. We actually have 1, 3, 2, 1, 3, 4, right? We have 2, 1, 3, we have 4 values. We have 4 values in it. Now what? We have 4 values that's in the original. Then that's divided by 2. So we can take those 4 values out. Take 1, 2, 3, 4. Take all of these out. And so these are in the changed, right? These are in the changed. So these are the candidates, because if you double it, it's in the changed as well. But we only want 3. So we need get the smallest. What if we do 1, 2, 3? No, we cannot do 1, 2, 3 because we have 4. If we do 1, 2, 3, that will be 2, 4, 6. There will be no 8. We sorted. Okay, so we know the smallest is 1. So double 1 must be in it. So 2 must be in it, right? So we can remove 2. And then the next is 3. So double 3 must be in it. Ah, that might work. That might actually work. So we go the smallest, and then the smallest double must be in it. So remove it, right? So now we find the next smallest, right? Because if you double, they must be small, and then we have the new value. So all we need is just get the smallest out, right? We get the smallest out, double it, and that will be the double. So we put it somewhere. And the next small pop up, we check, right? If it's the smallest, then we just skip. We'll go to the next one. And the next one, we do the same thing. And then we say if it's not, then we keep it, double it, so we put it in there, go to the next one. Okay, so we just need to sort it. So it's not too, I think I made a mistake. Yeah, made a mistake. It should be 1, 5, right? Yeah, it should be 1, 5. Too excited. All right, let's get this done. All right, so what do we have? We'll do this sort, and then we say original is a set. Actually, not original, it's doubled. Doubled is a set. Result is a list. Okay, and we say for C in changed, if C not in doubled, doubled dot add 2 times C, right? Double dot add 2 times C, and rest dot append C. If C is in doubled, then just skip. So we keep run this. At the time we end, right? And we say if len res equals len doubled and len res plus len doubled is equal to len changed, then we return res. Otherwise, we return nothing. Okay, try this. I mean, we can check a few things beforehand, right? So n equals len changed. That's fine. If n is not an even number, then return this. So that could be a easy check at the beginning. Changed. Okay. Yeah, because it works, because as we keep going, if something's not in doubled, then we put in double, right? And the result is gonna append. And eventually we'll have too many than double. Yeah, because it doesn't get removed. Okay, let's give this a shot. I don't know. What else can we try? Hey, that's a good one. 4, 8. No. 2, 4, 8, 4, 8, 16. I'm gonna try this one. Yup. That's a no. That's a no. 2, 4, 8. Good test case. That's interesting. What happened? So C not in doubled dot add. So double we have 4 in it. And next one 4. 4 is in doubled, so I just remove it. Next one 4. 4 is in doubled and then remove it. So it's not. Double need to be a counter. Right? Double counter is this plus equal 1. It's if doubled C, right, equal to 0. We can remove, right? Oh yeah, we can remove, don't need counter. Hold up. Let me try it again. It's a set, right? So if C not in double, we do this. Else, if C is in, then we should double dot remove C. So we can add it again. That doesn't make any sense, right? Doubled. 2, 4, 4. That's the first 4 is in. So C in doubled. So we remove 4. So next time 4 comes in, 4 not in. So we'll add 8. Double become 8. And then rest, and actually put the rest as well. Oh, well, we will remove the double. Oh, I think now we just say len is equal to this divided by 2. Right? Yeah, that's half. That should work. Hold on, let's remove this. Yep. So it's a complicated test case passed. What else can you think about? I don't know. Something like this. Let's try. Lots of repeat. Yep. We got another issue. This is good. We're basically doing it ourselves, so we're not relying on the test cases of a submission. All right, so what happened now? 1112. Now you see we need to be a counter, huh? Yep, has to be a counter. So if counter C, right, is equal to 0, which means it's not doubled. It's not a doubled value. Then doubled this plus equal 1, else doubled C minus equal 1. Still not right. Wait, hold on. Counter equal to 0. Counter C equal to 0. What the heck? Doubled. There you go. There we go. Yeah, I thought I can avoid counter. Turns out, cannot. Good test cases. What else? Now I tried lots of repeats. We tried 2, 4, 8. I have another evil idea. 3, 4, 5, 6. This is very evil. Oh, even evil works. Okay. Try this. Oh, it's the first time do this. Ay. Doesn't look. Oh, what was it say? It doesn't look nice, but we did pass. Okay. Why so slow though? I don't know, but it worked. That's not the best, but yeah, I'll take it. See, the extra 2 test cases is very important. Extremely important. 2007. So sort changed. Go from small to large. For each value, if it is not a previously doubled value, it must be the original value. We also double it and keep track of the doubled value. If it is a doubled value, we ignore it and remove its count from the track. At the end, check whether the number of original is equal to half of changed. Yeah. Yeah, this strategy works because doubling the original always ends up with some value not smaller than the original. Thus, if we go through changed in ascending order, we will always encounter the original, and as long as we ignore the doubled value, we will always encounter the original. O and login. Okay. One trick is to use counter to keep track. Right, to keep track of the doubled value because using a set does not work with repeated doubled value. So, okay. Let's see, what other methods are there? Smallest to biggest. Counter. We can do that. If counter x is larger than, doesn't make sense. The current value, the count, is larger than 2 times the count. Otherwise, 2 times the count minus this if x what is n, right? Oh, this is a loop to sort the key. I didn't see that. Get a counter first. Then will be sorted C. Interesting. If this count is larger than 2 times, well, it's the smaller value, right? If the smaller value, and we're guaranteed because we will remove the ones when we consider it, right? Because, yeah, if it's the starting value, then it must be. If it's equal, what does it matter? So now we're handling is CX, right? CX, and yeah, so every time we consider CX, so we have to remove 2 times it from it because those are no longer of consideration. If it's 0, then we need to remove half of it because CX is equal to C2 times X. Holy crap, this is very good. So that's the solution 2. Oh. Similar idea, but better implementation. Turn the entire change into a counter, then go from small to large keys. This way we speed things up by going through only unique keys. Now, for each key, 2 times key must not be smaller. Count. The count of 2 times must not be smaller than the count of key. And we also remove the count of key from the count of 2 times key whenever a key has been visited. Special case is for 0 because 2 times 0 equal to 0. Okay, so I think I can still do that. I'll still do that. Right, and then we say counter equals counter changed. And then for C in sorted counter, if counter C is larger than counter 2 times C, then we'll return. Yeah, because it's just not happening. Otherwise, say update counter 2 times C. Update the count of 2 times C. I say counter 2 times C minus equal to counter C. Yeah, because we have already considered C, so we didn't remove that many. But only if fx. Else it's counter C divided by 2. This is when C is 0. Also, treat C equal to 0 differently. Okay. Once we're done, I'll return list counter dot key. Ooh, that's why it says elements. Notice the use of elements. Nice solution. Elements. I think it'll be faster. A little bit. N plus k log k, where k is the size of counter. Alright, so that's that. We'll end this. Let's go to this one. So, the solution is DSU, okay? Is DSU. But the trick, so the difficult part that we have is if you have the meeting at the same time, right? Then if after this time, then everybody is connected to 0, then everybody's good. Everybody should share the secret. But the problem is if after a time you have someone that's not connecting to 0, right? And the issue is if at time 1, if we have 2 people not connecting to 0, and at time 2, one of those person becomes 0, and since they're still connected, then the other person will become 0 as well. So we need to avoid doing that. Therefore, we have this piece, which is very important, which means after we go through the same T, right? This current T is different from the previous T. Then we go through the people. Actually, I don't call this people. These are outsiders, right? Maybe it'll be easier to define them as outsider, right? They're the outsiders. So we go through the outsiders and see if any of them is not 0, which means any of them does not have the secret. If they do not have secret, we'll detach them from the disjoint union. We would detach them, right? So by detaching them, even if the pair that's supposed to be paired to this person later on gets the secret, this person will not get the secret. So we kind of solve the problem of this one, right? So we have 1, 2, they got together at time 2. 1, 3 gets together at time 3, and 3 has secret. So 1 has secret, but 1, 2 meets before 1, 3 meets. So 2 should not have secret. And that means at the end of 1, 2, it's as if they did not have any connections. So we have to remove their connection. So this is the detach. So that's one. Right? That's one trick. And the second trick is actually very important, is during the, and of course, detach just means we set the parent to itself and then we reduce the rank. So that's, just the detach. So this is important. We need to set a rank 0 to math.infinity. So the reason for this is because when we have a mismatch, like if both of them has appeared in the union and now we want to match them, we will compare their rank. But the rank is heavily determined by the order. Whichever pair happens first, they will have a higher rank. But that's not what we want. What we want is whenever someone's parent is 0, we want the other person to be 0 as well, which means 0 must have the heaviest weight. Therefore, we set this to math.infinity. So whenever 0 is involved in the union, they will always go to 0. So that's it. That's the two, kind of important part in this. And honestly, it's not that difficult, right? Yeah, and then we have this to make sure that we add the outsider at each right. So let me, this is a good problem. It is apparently my union fine, but there are two twists. First, we need to deal with the situation like this, right? With first person equal to 3. The first meeting is between 1 and 2. Neither has secret. Second meeting is between 3 and 1. So now 1 has secret. However, 2, the meeting, right, between 1 and 2 happens earlier. Thus, 2 still does not have secret, despite 1 having secret. If we use a naive union fine, right, where 1 and 2 are unioned, then when 1 and 3 are unioned, 2 would have been unioned with 3 as well, making him share secret. We must break such tie. Hence, during iteration of the meeting in ascending time order, whenever all the meeting, right, all the meetings of the same time, all the meetings at the same time have ended, right? If all the meetings of the same time have ended, we check to see any of the people involved. See if people involved does not share a secret. For such outsider, we must cut its tie, right, to any of the union before. Yeah. Second, we want anyone that union with someone else who has 0 as parent to also have 0 as parent. However, since the union is decided by the rank of the parent, it is likely the rank of 0 is lower than the rank of another parent if the other parent happens unioned ahead of time. Therefore, we must arbitrarily set the rank of 0 maximum, thus guaranteeing how do you spell guarantee? Guaranteeing that whoever unions with 0 with someone with parent as 0 also get 0 as parent. So yeah, that's the 2 tricks. If you go through, that's ON. Let's call it log n. This is actually log n. This is OK, because we don't know how many meetings we have. So OK log n. How about this? I don't know, depending on how many outsiders we have. The worst case, we go through n outsiders, right? I go through n outsiders. So OK n. So like what? OK ONK log n. I don't know. I just put it out there. Okay. Let's see. The smart people union find. Who don't know the secret. Yeah. M log M, the length of meetings. I don't think it's length of meetings. Iota? The heck is iota? That is easy to do. because there's no rank. Oh, sorting. Dude, forgot about sorting. Yeah, I just throw O n log n. M plus n log n. Yeah, we know it's m log, I'll say, oh no, m log m plus m log n for sure. But we have this portion. M plus n. Yeah, because this should become something times log n. And this is log n, so something plus something times log n. So OM this plus this plus this plus this plus this. M of this, yes, yep, makes sense. Time complexity inspired by yeah, I doubt that people actually know of a command function. Alpha. Okay, we do alpha n because ours is what's it called? Rank reduction? Path reduction. Path compression. Right? Path compression. So is it where m equals line meetings and alpha n is the inverse, no, is the inverse function of a command function which describe the time complexity of union find with path compression. I want to see what a command function is. Yep. Oh, it's during a contest. Wow. Oh yeah, it is during a contest. No, we'll not be able to solve this during a contest. Anyway, so we are at a good spot. All right, that will be it. Very happy that we solved this. Let's pick the next one before we end. Medium, that's good. Yep. I'll see you guys tomorrow. Adios.